request all participants to kindly settle down. We are going to start now. So a very good afternoon to all the participants from various colleges for coming here, as well as participants from our college, respected faculty members, principal sir, principal madam, and today's eminent speaker, myself Dr. Amit Kumar Vashne, Associate Professor from Department of Electronics and Communication Engineering, welcome all of you in the course lunch session of the 4th day of the 6th-day Atal sponsored Atal FDP on AI for Healthcare Excellence, Innovations, Challenges and Future Prospects, hosted by SIMT Supreme Knowledge Foundation. Now, like previous sessions, once again today we are privileged and fortunate to have amongst us an eminent speaker from world-renowned institute, Banaras Hindu University, Varanasi. The speaker is Professor Manjari Gupta from the Department of Computer Science, BHU, Varanasi. I welcome you, ma'am. A very big round of applause. Okay, I welcome you, ma'am. We are very thankful to you for coming here, for giving the presentation despite your busy schedule. Okay. Now I welcome you, ma'am, to this institution. We are very thankful to you. Now, before we proceed for the felicitation round, I would like to give a brief biography about her. Now, Professor Manjari Gupta is Professor, Department of Computer Science, Banaras Hindu University, Varanasi. She completed her BSc and MSc from University of Allahabad in 1999 and 2002 respectively, followed by PhD in 2006 from Banaras Hindu University. She joined as teaching assistant in BHU in 2004. Then she joined as a lecturer in IIIT Allahabad in 2006. She joined BHU in 2007 as assistant professor, where she was promoted to associate professor in 2017 and as a professor in 2021. Now, her research interests include software engineering, artificial intelligence, healthcare and computer vision. Now, she has executed over 5 research projects funded by MHRD, India Knowledge System Division, Ministry of Education, IOE, BHU and DST, New Delhi. Now, she has over 95 plus papers in reputed journals and conferences, which includes book chapters. She has supervised around 9 PhD scholars in her field. She is a member of IEEE Women in Engineering, life member of Computer Society of India, reviewer in many SCI and Scopus Index journals. She received Visiting Professor Award by University of Toulouse, France in 2025 and several international travel support to present papers in various international conferences. She qualified UCG JRF NET in June 2005 award by UGC in 2005 and qualified GATE award by AICTE in 2002. Now, she has held various administrative positions, like she was the course coordinator for MSc Computational Science and Applications. She was placement coordinator, member of training and placement committee. But the most important is in 2023, she became coordinator of DST CIMS, Center for Interdisciplinary Mathematical Sciences, Institute of Science, BHU, Varanasi, and she is holding this course now also. So, with this wonderful profile, now we would like to have felicitation. So I would request our principal, sir, principal SIM team and departmental chair of CSC, IT and EC studies, Professor Dr. Jogashis sir, along with our principal SKFGI, Professor Dr. Tripti Gun Krishnas madam, principal of SKFGI and Chief Administrative Officer SKF, to kindly come forward and do the honors along with the coordinators of this FDP, coordinator Dr. Mosumi Otta madam and coordinator Dr. Uttara Basu madam, to kindly come forward and do the honors for the felicitation. Sir and madam, please. She will be felicitated with pictorial. So we have our principal madam, Srifti madam, Srifti Gun Vishwas madam, felicitating with the pictorial. Our coordinator of FTP, Mosumi Ottar, bearing the badge to the eminent speaker. A very big round of applause. Now our co-coordinator of FTP and principal madam, Prithvi madam, presenting the memento to the eminent speaker. A big round of applause. Thank you, sir and madam. Now today she will be speaking on role of AI in bio-retina. So I request all participants to gain lot of knowledge out of her speech. Now before madam proceeds, I would like to request our principal sir, Jogashis sir, to say a few words about her. Sir, please.
On behalf of Supreme Knowledge Foundation, on behalf of both of us, me and my colleague Tripti madam and the entire teaching fraternity, madam, our sincere thanks and gratitude to you, not only for presenting the today's talk, that is going to be an excellent session, but accepting our invitation to stay in our campus as a guest. That actually reminds us you came from a place, Varanasi, which is not far from Nalanda. So that was the practice at ancient time, that the professors from around the globe, they used to come here and then do this. Only unfortunate thing is that we are actually, vacation is going on, so students are not here. But still, some students have shown interest to interact with you. So maybe tomorrow we can have. And madam, we are honored as you are staying along with family in our campus for this. Thank you very much, madam.
Madam, now the floor is yours. You can start now.
First of all, I want to give my thanks to Jogashis sir, who invited me for this talk in this FDP, and I am really very happy to see that this type of FDP are being organized in different institutions, and teachers are improving and they try to learn and they try to update themselves. Although nowadays we have a lot of other ways like NPTEL and Coursera, ADX, but when we update our in this way in a single room, when we sit all together, we discuss with each other, it is always very different from the other like STEM and NPTEL courses. And that's why we see now NEP also in new education policy. So government is saying that the students can take 40% papers from STEM and NPTEL. But if we see, at least in BHU, when we float courses and we give options, then students always they want to take courses that are taught by the teachers of BHU. They don't want to prefer STEM courses, but since teachers are overburdened, and this is the policy like this. This is very means canteen person is very. He always asks, ma'am, what do you want to take? If these my daughters are also with me, so he's taking care of them also. So it is really very nice. I am very happy and thank you for inviting me. So the job that I was given was to talk on role of AI in bio-retina, but I will speak on bio-retina as well as some other diseases on which I work, that is neurological and cardiovascular diseases prediction. So not only bio-retina, I will talk about these things also. So first of all, we see there is a role of AI in bio-retina systems or in many other diseases or in general any field of computer science or other fields also. So we see there is a lot of nowadays techniques of AI we are using in different domains or in different fields. So if we talk particularly about bio-retinal system, in that case, these are the few things. These are the things where AI is being used. So first of all, visual signal interpretation. So if there is some problem in retina or some parts of that, so in that case it is necessary to have, in that case generally nowadays AI is being used for visual signal interpretation. So if signals are coming but your retina or if retina is not able to transfer those things, those signals to the brain, so in that case it is necessary to interpret them. And nowadays we are having deep learning techniques that is very easily mimicking the properties or functions of retina. So we'll see some things in detail, or at least one model that is doing like this. And the second thing is AI for diagnosis and prediction. So this is so we can say that we can see the role of AI in two. If we talk about retina, so there in two ways AI is helping in this field. One is if we have some prosthetic retina or some component of that. So if it is not working, then we can have this type of, and that component is having AI, and AI is working or functioning like the real organ itself. The second thing is if some changes are being done or some degradation is there in any organ, then if AI can, although doctors are there, but since now we are having lot of scans, lot of tests and lot of imaging. So in the previous session also we have seen nowadays lot of instruments are there that can get different tests and images from our organs or our bodies, but it is very difficult because we don't have a specialist to understand that. We may have doctors, but nowadays doctors are also many times they don't diagnose the correct disease, and that's why it is necessary or it is very good if we have some technique like AI or deep learning techniques, because we are seeing that medical imaging can be to interpret medical images. Nowadays deep learning is working very well. So we'll see how it is being done and what are different models for that. So here in case of retina, basically OCT and fundus imaging, these are the two type of data, two type of images that are generally taken as it does, and doctors see these to identify whether the retina is working properly or not, or what some other some degeneration is going on there. So same thing, same input is given to AI or deep learning or ensemble learning techniques or simple machine learning techniques. So we should have some number of fundus imaging, so number of this data set or number of OCT images if we are having. But in that case we need to have some annotations also, that in which part, which particular disease or which particular functioning is there, and based on that if we can train our model and then we can predict. So we will see there are lots of things. There is already, it is not the case that we are develop some deep learning models or AI models. Field is already grown up. Many deep learning and other AI techniques and tools are there. For example, IR and Google's DeepMind for diabetic retinopathy. So these I have given only 2 examples, but there are lots of other examples that you can find on internet. These are very good tools to identify diseases or not only diabetic retinopathy. I have written only this, but DeepMind, Google's DeepMind is identifying other diseases of eye or retina also. So we'll see how it is doing there. How it is means what is the architecture of this that is behind the Google's DeepMind. So first, for the sake of complexity, I have included these slides in my presentation. That what is the basics of vision and human retina, what is the structure of eye and retina, what is the functions of photoreceptors and other cells, then retinal signal processing, how the retina is working, how the brain is getting signals, and so that image is being formed and we can see whatever we are seeing. And then what are different retina disorders? So few are written here, but there are many other things also. Then what is bio-retina? So bio-retina is totally the concept. This concept is totally different. I initially told that there are 2 ways where AI can help in retina. So one is bio-retina. So bio-retina is nothing related to the identification of disease from the data set of eye or eye scans. That is basically if something, some degeneration happened in the retina or in any component of eye, in that case we must have some prosthetic retinals. And in that case, these prosthetic retinals will be AI based, so they will be able to interpret your signals, and they will be helping in how to see, how to for blind people or for old persons, whatever, if they are having some disease, so they will help them. But so this is a totally different field, and I'm not going in deep here. I am basically I will talk about the second part where we can identify disease. We can identify disease using deep learning. Of course, for that we must have some data sets, and we have seen in case of eye we must have fundus images, or so that is 2D images, and the second type of images data that is OCT images, but it is basically 3D. So of course OCT image is having large amount of data, and for doctors also it is very difficult to actually understand and identify what is the actual, where is the disease, where is some extra fluid, where is some lesion, or where is some degeneration in that particular part. But that's why now researchers want, if we have deep learning technique, because deep learning are very, nowadays we have different deep learning architectures that are easily capable of understanding these any images, and in case of, particularly in case of medical images. So we will see the architecture of that. So I'm leaving these slides. I just kept these slides for the sake of completeness. What is retina, anatomy of human eyes, so cornea, pupil, and we know all of these are having different functions. Then retina as a light processing sensor. There are different type of cells that are very important in retina, and so these are rods and cones. So all are having different types, different functions. So of course doctors know it very well, and if we are trying to generate bio-retina, if we are trying to simulate bio-retina, we must know all these components, all these cells of retina, all these things in very detail. But if my talk is towards the identification or detecting disease, so I am leaving these things and directly come here where we will talk about basically this this Google's DeepMind for diabetic retinopathy and age-related this disease prediction. So what is this here? I already told you that fundus images are there. Fundus images we must have. Generally doctors do like this. We have fundus images or OCT scans, and doctors try to find out from these images whether some degeneration or diabetic retinopathy or any other type of problem is there in your eye or not. So nowadays there are lots of other tools are there. One of them is Google's DeepMind that I have chosen for today's talk. So you'll see how Google's DeepMind is used for identifying diabetic retinopathy and AMD disease. There are lots of other also. So diabetic retinopathy, we know what is this. So generally it is a complication of diabetes causing damages to retinal blood vessels, and it is very difficult to find out using these fundus images or OCT scale. It is not the case that if we get this for any diabetic person, then doctors will easily identify it. It is generally difficult to identify it. If some experienced doctors are there, then of course they can find it, but generally we have not such a specialist. So there are chances that they may leave, they may not get, they may not be able to understand these scans, and that's why this is going on there. So early signs are there, vision loss and blindness if it is undetected. These are the problems, and because of that deep learning techniques are being used here. And then the second one where this Google's mind is also working, that is age-related macular degeneration. So macula is the part of the central part of the retina where image is formed. So if some problem occurs in macular, in that case that image is not generated in that good way. And so this is another. So this is generally age-related problem, and this Google's DeepMind is working for both of these two diseases. So generally in Google's DeepMind, basically it is trained on optical coherence tomography, OCT. It is not fundus photography is also there, but it is 2D. As I already told, this is 3D data, and in 3D data there is a lot of data, and that's why for doctors also, because there are different cross-sectional layers of this retina, and so data is in that form. So it is very difficult to combine and then see and understand whether disease is there or not. So medical, through this medical imaging, lots of tools are being developed. So now we will see what is the DeepMind AI system that I am talking about. So this is of course while it is developed, the problem was growing patient load. We have a lot of doctors, a lot of hospitals, but very less doctors who are very experienced, where we are having faith in that time. I was discussing with someone because I am working on medical now in healthcare. So in BHU also we are having IMS, Institute of Management. So we are having basically hospital, and where doctors are involved in these clinics as well as they teach students. But you see BHU, and that is very renowned hospital. Even then we are faculty in BHU, and we always think twice to go to them, because a lot of us have the experience that we are having some. If we are having some problem and we are going to doctors are not able to diagnose successfully. For example, I want to share two examples of BHU. Although I say those are very good doctors, but the problem is, if you see in BHU, when we go there, lots of patients are there. From morning 6 o'clock they are in queue, and when we go there, this type of hall is totally full. And so they are heavily loaded, and it is very difficult for them to give attention to a particular patient. So I am telling you, my elder daughter, she was lactose intolerance problem was there with her. But when I go to the doctor and in BHO itself, because that time I was also new and I thought this is my university hospital, so I should go there, and I went there. And I don't know why they could not diagnose it, and they gave all the antibiotics, high antibiotics, and they gave the full course of 1B. And after that, the doctor told me that now this is over, this treatment is over, and you can go with her to your home. So I told, but the condition is same. Actually, she was having, means after 5 minutes or before that, she is having some, you know, in lactose intolerance. So the same condition was there that time also. So after heavy lot of means highest dose of antibiotic, she is in the same condition. So I came there, and my elder daughter, she was in Varanasi, and she was in Varanasi. So that is a very small state and a small city, and there was a hospital, and she told, okay, you come here because there is a one doctor who gives lot of time, so we have satisfaction, and generally we tell everything with him and to him, and he gave a very good, very less, and the medicine that always works. So I went there. My daughter was only around 1 month, and he told that it may be problem of infection, but there may be problem of lactose intolerance also. So you see that the IMS BHO doctor, he only identified, he only guessed that this is a case of infection. He didn't, he would not imagine that there may be problem of lactose intolerance also. While a simple doctor in a hospital in Varanasi, because he was free, he was working, updating on him, he was getting time, he can think lot of things. So this is the problem that nowadays doctors are very much overloaded, and because of that they may not use their capability, and they are not able to diagnose properly. And because of that we are in the same way, I am telling you, in BHU we have IIT BHU also. So in IIT BHU, in Department of Computer Science and Engineering, there is Professor Ravi Shankar Singh. So he is our colleague. So he told, once he met me, and he told, I am very disturbed because I told what happened. So he told, my wife is in IMS hospital. So earlier they diagnosed that it is TB. So she has taken the full course of 9 months, and after that she went there, and again they are telling it is they told it is TB. So she has again taken the 9 month course, and third time also they are saying. So maybe he shouted, and because it is very difficult. Third time he is saying the same disease your wife is having, while so she may have some symptoms, because of that they may be going, and it was totally some disease that is very rare disease, not very critical, but of course it is very rare. We were not knowing what is that disease. He was also not knowing, so he went Chandigarh, and then it was diagnosed. But you see, this happens with many of us, not to all, but it happens with many of us, and that's why researchers and we are seeing AI is being used in this medical field also, because we want at least we should have good diagnosis.
Can I ask?
Yeah.
You were talking about diabetic retinopathy. Is it mandatory a patient? See, it's an ocular disease detection, right? In ocular disease detection, you have a glaucoma, you have a dry eyes.
Lots of, not only
yeah.
actually deep mind system is only developed for identifying.
For example, a patient who does not have developed any diabetic symptom cannot have diabetic retinopathy, right?
No. There are same symptoms or same disease may be there. It is only this is not my area. I have seen deep mind.
I am also not from.
I am saying you, deep mind is developed for identifying diabetic age-related molecular
My question is that,
So
you
that-
take a fundus image, right?
Yeah.
So you are going for an ocular surface. It's about ocular surface disease
Yeah.
detection.
Yeah.
So for example, I'm sometimes due to BP and I some experience a red eye and all.
Yeah.
So I take a picture.
Yeah.
And if I give it to a system, is it a mild means DR or is it a, in stages of DR there are 6 stages of DR, right? Non DR to stages of DR. Now, which means how it is detected if I don't have a diabetic symptom anywhere. So in the system it is not feeded, right?
Yeah.
So is it that is disease, when the disease detected, is it something that the prehistory of diabetic need to be known or?
Of course, the NEI system we are giving multi-model data that will be very good. That can work very good. But if we are providing only suppose this
Images,
scan
yes.
image or yes, so of course there are chances that it may not detect. Correct. Yeah. So if we are giving some clinical history also.
Because picture looks same for all
yeah,
sometimes.
maybe same for
Same
that.
for
That's why
ocular disease, yeah.
that's why you see that I will show you the accuracy. Accuracy is not also not 100%. It is also 94% around is there in this. I will show you. Later it is there. So I will show you. Accuracy is also not, but all the big companies are working on this so that we generally listen that after 5 years or after 10 years medical science will be very good because of AI, and AI is helping a lot, and definitely we will live long, we will live very without diseases also. So we should think on how, or at least maybe our next generation. So your medical science will be very good because of AI. So nowadays it is, we can say it is not in the 100% accuracy case, it is 95%, but after few years it will be very good. So I am just saying one of the tool that is being that have been developed using Google itself, that is DeepMind, and it was because of growing patient load, shortage of retinal specialists. So there may be some doctors, but they may not diagnose properly. And then their manual grading is slow. As the first speaker in the first session, he also told that it is taking a lot of time if we are doing manually, or if we have some device or some instrument, then it can be done in very quickly. So that's why the goal was to build an AI system that can accurately detect and recommend treatment for this. So you see there also, they are not only detecting, they are referring, they are giving whether it is urgent case, whether it is a critical case, whether it is a simple, they can go to doctor and see it near future. It is so the output is disease diagnosis, urgency of referral also. So they are giving this also, and then confidence score, whether the model, how much confident this model is also. So these are the 3 things they are giving. And this system was developed in collaboration with one of the eye hospital of UK. So they uses deep learning, basically CNN based architecture is there. So it is trained on thousands of OCT and fundus images, and so this OCT basic scan is 3D scan. So this Google's DeepMind is basically working in 2 stages. In the first stage, it is doing segmentation from the OCT images, and after segmentation, whatever output is there from that, features are being extracted, and in the second stage, classification is being on there. So whether the person is having some diabetic retinopathy, or the person is having this other disease, or the person is healthy. So this type of classification is being in the second stage. So you see the model is working in two stages. The first stage is anatomical segmentation, the second stage is disease classification. So you have fundus image or you have OCT image. So in the first stage, means your deep learning model is working in two stages. In the first stage, the segmentation is done on these images or these scans. So segmentation model is used to identify retinal layers, pathological features, whether some lesions are there, whether some fluids are there. So those segmentations are being done. Then based on those segmentations, features are being generated. And then your in classification model, they have used gradient based boosting model. So in segmentation, we already know that UNet and deep lab style, these are two advanced models of that are built on top of CNN. So these are used for segmentation. These are very good models for segmentation, for basically image segmentation, and that's why the same UNet and deep lab style CNN is being used in the first stage of this DeepMind tool. So here segmentation, the first stage purpose is it segments important anatomical structures and disease features from this OCT images. So it segments, if lesions are there, it segments the retinal thickness. So based on the retinal thickness, retinal layers, it identifies presence or absence of pathology markers. So different pathology markers, and so lots of different features are being generated based in this image after segmentation. And then there are lots of other data sets also if some wants to work on. These are for segmentation itself. These are some medical imaging databases where you can apply some other deep learning segmentation models itself. So we have seen OCT and fundus data, that images data that was used in Google's DeepMind. But these are some other data also where segmentation, if you want to work on this first phase of this model, you want to apply different segmentation techniques, then you can use these other data sets also. Then the second part of this DeepMind tool was classification or reference models. So here they have used gradient boosted decision trees, so or XGBoost basically. So its purpose is to first of all classify patient scan into one of the three reference conditions categories, whether it is a routine type or urgent or observation. So decision is basically means you are in the first phase, you are getting lots of features and you are training your gradient boosted decision tree on these features to identify what is the whether disease is there or not, and if it is there, what is the referral category, what should be the referral category. So gradient boosting algorithm, there are lots of machine learning algorithms, but this why I choose this DeepMind tool. There are lots of other tools. There were lots of other tools also, but since here for the classification purpose, they use gradient boosting algorithm, and gradient boosting algorithm is one of the ensemble learning technique that is being used, and it is working in most of the classification problems. It is working very well, but generally people don't know the basics of this gradient boosting algorithm, and that's why I thought I should it would be good if I would talk about this gradient boosting algorithm. So what is this gradient boosting algorithm? Of course, it is a supervised machine learning technique, and it is used for classification as well as regression problems. So and it is an ensemble learning technique. I hope all of you are aware of ensemble learning technique. So for classification as well as regression, generally we have different machine learning models. So if we are applying a single machine learning model for suppose classification case, then we say what is the particular model. Suppose it is a decision tree model or SPM model or any model that we are applying. And if it is an ensemble learning model, then what happens? We are not relying only on a single model. So we are assuming that single models many models, all these models are weak models and they are not giving us the accurate result, and that's why we will not rely only on a single model. We will train different models on the same data set, and then we will finally get the result by seeing result of all these models. So this is the basic concept of ensemble learning. So we assume we are having lot of weak learners, lot of weak base models, and then we will train all these base models, and then finally our final output will be based on the output of all these base models or weak learners. So let us see how this gradient boosting works. So as I already told you, gradient boosting relies on the ability that best possible next model. So basically there are other type of ensemble learning also, that is bagging. So there are two types of ensemble learning technique, bagging and boosting. So in bagging what we do, I told you that in any ensemble learning technique what we are doing, we are not relying only on a single model. We are working with several models, and then final result we are giving by seeing result of all these models. So there are two types of ensemble learning technique. One is bagging, another is boosting. So in bagging what we do, we parallelly train all these different models, and then whatever result we are getting, we are taking final result based on that. So we can say that bagging is good in the sense parallelly we are training all the weak learners or base models, and that's why your model is very fast. While in gradient boosting what happens, we learn all these models sequentially. So first model we will learn first, and then we will learn the second model, then we will learn the third model, and so difficulty is that, or we can say that the drawback of this type of learning, that is this type of learning is called as the boosting learning. So the problem is that it is time taking, because we are training each model sequentially, so that definitely your model will be taking long time. But what is the advantage of that? Advantage is that the next model is working on those instances where the previous model was not correct. So previous model has learned the features and then it predicted values for all the instances. So for many of these instances it may be correct, but for suppose 20% of the instances it is not giving you the correct result. So your next model will work on this in these remaining 20% of the data set. So this is the idea behind gradient boosting. You see, suppose this is the data set and this is your model. First weak learner or base model. So you are training it, and for data set where your model is giving errors, your model is not accurately giving the answers, your next model will basically work on those. So it will concentrate on those more where errors were there for the first model. So in the same way, sequentially we will learn many base models, many weak learners, but finally the last model will give you the best result, because it is taking care of all the errors that were interpreted because of the previous model. So let us do how it is done. So same, you see this is a very simple model and it is used in DeepMind's Google's DeepMind tool for identifying whether the disease is that particular disease is there or not. So let us take a very simple example. I am not taking that image, or because in that case it would be difficult to understand this gradient boosting algorithm. So what is this? Suppose this is a very simple example. We are taking only 4 features. One is age, another is some area in square feet, and then location, and then price. So price is suppose our dependent variable, and rest of these are independent variables. So this is the of course this is the regression problem. It is not the classification problem. It is regression problem. But your gradient boosting algorithm can be used for classification as well as regression. So now we can say that there are 3 independent variables and 1 dependent variable, and we want to learn for each and every instance we want to learn the value of price depending on these independent variables. So how this gradient boosting is done? In gradient boosting, what we do, we take the average of the values in the variable that we want to predict. So we have taken average of this price, and now we are assuming that this is the price for all the instances, and now we can see, we can check if this is the actual price, suppose, or basically this is the actual price. So we can say that if our model is predicting this one, then what will be the error for each and every instance? So error will be difference of these. So if we will take difference of actual price and average price, we will get the residual. So we will find residual for each and every instance. Okay, and then what we will learn in other machine learning models or deep learning models, how we learn? We learn on the actual given data. We learn on this data, we try to find out what will be the price for the given instance. While in case of gradient boosting algorithm, where what we learn, from which data we learn, we don't take the actual price, we take residual in place of this price. So what we are trying to learn, that how much difference is there with the actual, and if we are assuming that this was the difference learned by the previous model. So previous model has done this much mistake. So next model should try to learn in the way such that this residue should be now zero. So in this way gradient boosting is done. So this was the how we will learn. We will learn on this data, and this is gradient boosting decision tree. So gradient boosting decision tree is based on the decision tree. I hope all of you are aware of decision tree model of machine learning. So in decision tree, how we do the learning? We learn by one we identify the best attribute or best feature and its value, and then we check what will be the class value, or what will be the actual value of the dependent value. Like if square feet is greater than some value, then the second attribute is location. So if the location is greater than something, then this is the output. If square feet is greater than x and age is also greater than x, then this is the output. So in this way your model learns. So your model learns basically lot of conditions, and based on these when new instance is coming, you check these conditions, and based on that you find what is the value of the dependent variable. In this way decision tree works. So here also your first model means first model that will be created, first decision tree model that will be created will be like this. So here what can happen, in the leaf nodes there may be only single residual, or there may be more than two residuals. For example, you see here, if square feet is greater than x and location is greater than, if square feet is less than equal to x and location is less than z, then these are satisfied by two instances. These conditions are satisfied by two instances, and for these two instances, whatever residual are there, you will keep these two residuals in the limit node. So what we will do, we will take the average of this. We will take average of this, and in this way we will get the exact value in different leaves. And now you can say you are getting, you have taken average, so you are now getting in each and every leaf you are having only single value. So now you can predict whatever new instance is coming, you will say, okay, you will check what is the square feet value of that, what is the location, or what is the age. So wherever it goes, you will actually predict the residual of that. So now in the next step, what we will do, we will predict the price of average price plus there is a learning rate. So learning rate is one of the hyperparameter of this gradient boosting algorithm. So learning rate is suppose 0.1 into whatever the residual that is predicted. So in this way we will predict the actual price. So whatever, suppose this decision tree is being created in the next model, in the next stage this decision tree is created, and suppose we are stopping there, because we can have number of average price plus learning rate into whatever residual you are getting from this decision tree. If your whatever results you are getting, you are not confident on that, then we will add one more layer, means we will again take one more weak learner. So in that case, whatever residuals you are having, you will train again. Whatever values you are getting, you will find the new residuals and you will train it again. So after training, whatever tree you are getting, you will do like this average. So if suppose n number of weak learners are there, so you will get the actual price like this, average price plus learning rate into residual predicted by the first decision tree plus the learning rate into residual predicted by the second price, so second decision tree. So in this way you will get the actual. So this is very simple ensemble machine learning technique, but very powerful. You will see random forest is itself very powerful. If you see most of the researches, so you see SVM and random forest, these are two very powerful simple machine learning techniques. Lots of deep learning techniques are being used. Why we use deep learning technique when we have machine learning techniques also? We have machine learning techniques and very powerful machine learning techniques, and why we want to use deep learning technique only to show that we have used deep learning techniques. What is there should be some reason. Because if your data set is very large, in that case it is not means your machine learning model will take a lot of time and it may not handle that much of data, and that's why we need deep learning technique. So otherwise we have most of the at least these two, SVM and random forest, and ensemble random forest for decision tree or any ensemble learning technique that is based on the decision tree. These are very powerful machine learning techniques, and that's why you see in the deep minds they also use this one. So I have taken some simple example where I have shown that how it is working. Now again on the deep minds, so what is the deep minds contribution? You see generally, so here we also used deep learning technique in the first stage. In the first stage we were using CNN, basically unit based CNN for segmentation. So generally what happens when we use deep learning techniques, we say it is black box. It is black box. Why we are getting result like this, we don't know. Because this is how it is finding out features, we don't know. Lot of features we are getting, but we don't know what are these features, what are the what is the impact of these features, we don't know. We directly after identifying the features, it gives you the, when you apply the classification there, it gives you the final results. So generally deep learning techniques are black box techniques, but in this case what happens, we are having segmentation and the image is segmented in different parts, and it is totally based on the same idea that doctors do. Doctors also see the scan and they try to identify where is lesion, where is some fluid, where is some swelling in that particular organ. So same thing is done here also in this particular model also. So since they are doing segmentation, so when this segmentation is being done by the model, doctors can see those things, and it will be very very easy for them also to associate, okay, yeah, it is this model is giving us the correct result because it is showing and actually this segmentation is corresponding to this particular thing. So that's why we say that it is this deep minds tool for diabetic retinopathy and other diseases. This is transparency is also there. Performance.
I was saying that this is an independent model, or is it integrated with the OCT evaluation?
Integrated, this means it is already trained, and if we want to use it, we can, means of course we need to get output for a new instance, so we will run it for our OCT and it will give us.
We have to give the OCT and they will
Yeah, if you want to get on, otherwise you can use the training, their training data itself. it must be there. So before segmentation, they must be doing it. So performance, they are claiming that it matches outperforms leading retinal specialists, but I have seen the accuracy was 94%. So of course in doctor's case also it is not 100%. So speed, of course, it makes decision within seconds, while if you go to the doctor, it takes at least half of the day to get, and then they suggest some test, and so at least 1 week, after 1 week we get what is the active case. And then it is 3D OCTs, there are many other systems that are trained on fundus photos or fundus images, so it is OCT based, so it is giving you better results. And I told you that there are two main stages. So first stage was segmentation, second was classification. So I told you for segmentation they use a unit like CNN, and for classification they use exibus, and for explainability they used silencing maps. So basically silencing maps are generated after the segmentation. So using, and after that they use this red cam for explain it. Although if you are getting segmentation, so segmentation itself for doctors it is very easy to understand by, okay, this is the output, and using the intermediate output that we are getting after the first stage, that are the segmentation, so they can identify, okay, why it is the output. So I'm just waiting here, you see. So its accuracy or impact and evaluation. So 94 to 99% they are claiming, but we always keep this count, lower bound. So 94%. And this is the original paper for this deep fine this. So if you want to work on this direction, you can see this is 2018 paper. And in 2018 paper, so this is the base paper. There are, after that there are 2-3 more papers where you can get the idea of this whole deep fine, Google's deep fine tool. And so basically we have seen Google's deep fine tool for diabetic retinopathy and other disease prediction. But always if you talk to doctors, or they talk about data privacy and security. For example, in the first session we have seen there is resource person. So he generated some synthetic data. So when I went for my academic collaboration in Norway, so there also in one of the AI labs they were generating synthetic data for medical imaging itself. But when I came here and I thought I will also work on this. So here doctors are saying because this is a synthetic data, so who will believe on this? So this is what happens in India, it is sometimes possible that we are getting the patient's data, but in Europe there is a clear policy that we can't get patient's data. So they are and that's why they are generating the synthetic data. But in it is very, of course there is a data privacy and security. So when we talk about when we will use deep learning and AI for medical imaging and diagnosis of this, but data privacy and security is one of the concern. And biases in training data. So of course in AI we have biases. So it is very difficult. You may have data bias, you may have algorithm bias, and it is very difficult to. Sometimes we know that there is a bias, even then we ignore it, so that we can say that our model is working very well and we are having this type of accuracy. While there may be some biases in algorithm or data. So this is this is another challenge. And explainability in critical care. So as I have shown in Google's DeepMind, this is one of the very best tool in this way, because there you have the explainability. Why you are getting this type of result? Because in the first stage they are having segmentation, and that output, if doctors will see, it will be easy for them to believe on this tool. Okay, this result is it is saying that this diabetic retinopathy is there, and it is actually showing it here. So we should always generate deep learning or AI models where explainability is there. Otherwise, community or doctors, customers may not believe on that. told you this tool or any other tool that we are generating for medical disease diagnosis or anything, it should be AI, it should be used as an assistant, not for the replacement, because we know that human intelligence is always, at least now, it is not possible that your AI tool can surpass the human intelligence or doctors. So there are basically three criteria that must be satisfied. Then only we will say that we can replace doctors and we can fully believe on this AI-based medical domain tools. So what are these three criteria? So AI must generalize new population. So basically it is on whatever data we have trained and data that we use for testing. Suppose your model is working very well on this trained data and test data, but if you are getting some new data, whether your model is working on that new data also or not. If it is working on that, then your model is enough generalized. Otherwise, we will say that no, means your model is not generalized. It is working for that data that you have used for training as well as testing. But now, so there may be concept drift, new data that is coming that may be different. Because of that, your model may not be working or your model may not be generalized. In both of these two cases, you need to work on your deep learning or AI-based models. So this is the first criteria that must be satisfied, that your model should be generalized. Your model should not, means you will say that, you are saying that I have trained on this data, I have tested on this data and your accuracy is this much. So 100% accuracy I am getting in each and every, you are having suppose 5-fold cross validation and lot of techniques you have used and you are telling that 100% accuracy I am getting. So then it is not sufficient. You need to wait for the new data, and after some time when you will test on many unseen data, then only you will check whether your model is generalized or not. The second one is AI tool must be applicable to real world scans. As I told you, synthetic data, so there are lots of your model may work on the synthetic data but not on the real scans. And the third is AI must work and exceed the performance of human experts. So when all of these three criteria will be met by the AI tool that you have developed for medical domain in particular, otherwise in any area, then only you will say that, you can say that the AI tool can replace human intelligence. So this was the first part of my talk. So this was very difficult for me because I am not expert of bio-retina or eye disease itself. Now the second part is on my work, so I am more comfortable on this. So what is this? This is diagnosis of neurological disease from EEG signals using artificial intelligence tools. So it is again same. We are also trying to diagnose diseases, but which type of diseases? Neurological diseases. And what is the input data? Input data is basically EEG signals. So EEG signals, so then, we have EEG device. So I want to first of show you what is neuroscience. So neuroscience is basically science of the study of nervous system consisting of brain, spinal cord and peripheral nervous system. So your brain has a lot of components and basically cerebrum is one of the largest part, and again these slides I included for the sake of completeness. It is not necessary to know all these things if you want to apply AI in neurological disease prediction, but it will always be good if you know all these things. You will be able to generate more good models. So frontal lobe, parietal lobe, temporal lobe and occipital lobe. So each lobe has different capability, or you can say that you know that some people are very good in thinking, planning and all these, so their frontal lobe part of the cerebrum of your brain is very good. And then touch, smell, this is our senses, this is responsible for the senses. For memories, this is the temporal lobe, and for visual activity, this occipital lobe. So these are the four memory parts. And then this is also very important if somebody wants to work on neurological diseases, because in particular if they want to use EEG data set. So in brain what happens, whenever we are doing something or we are thinking something or we are we are doing some problem solving activities, whatever we are doing, some electrical activities are going on there. So then frequencies we can capture from EEG device. So they are mainly these, you see here, these 5 brain frequencies. So when we are in the sleep mode or in the dreaming mode, then delta wave frequency you can get if we use the EEG data. So from EEG data when you will capture, so the data wave you will capture in that case. If you are in light sleep or drowsiness or early stage of sleep, the theta wave is there. So this is 4 to 7 Hz. And if you are relaxed, wakefulness or means you are not sleeping as well as you are not doing much brain activity, then alpha is there. If you are busy and active in that case, it is a theta wave. So you see this is 12 to 30 Hz. And if you are doing problem solving or cognitive activity you are doing, in that case, there will be some gamma wave. So this is 30 to 50 Hz. So when you will record these waves, these frequencies from EEG device, you may get other frequencies also. So whenever we want to work on some neurological diseases, so we basically work on only these frequencies. So of course, depending on when we are working on depression, so we concentrate on some frequencies. If we are working on some other disease, we may concentrate on other. And sometimes some other things, it is some other diseases, there are possibility that all of the brain frequencies are there may be effect of that. So we may work on, we may take all these frequencies in our data. So these are the 2 ways to collect brain signals, these waves frequencies. So invasive and non-invasive. Invasive is EEG and MEG and fMRI also. Non-invasive techniques are also there, but of course as a researcher when we don't use non-invasive techniques, invasive techniques, we use non-invasive simple techniques where patient can or any human being from there for which we want to get data, he should not feel awkward, and he should be ready for it should be easy for him to give the data. So we use non-invasive techniques. So EEG, fMRI and MEG. So I mainly work on the EEG data. So how EEG, so there is different types of EEG means there are different devices from which we can collect EEG data from the persons. So you see there are different electrodes and its positions are also written. So this is on the right part of brain. In the same, whatever positions are given, we need to place these electrodes on the same place. And on the left hand side of brain, these are the electrodes. So of course, in different type of devices, you may have different number of electrodes. So generally, we don't work on this. This is a very heavy EEG machine. Otherwise, there are some portable EEG machines also, where we have only few electrodes. And these electrodes captures electrical signals from the brain at that particular region. So generally we work on 16 or maximum 32 EEG, or we say it as a channel. So one electrode gives you one channel. So if it is a 16 electrode EEG device, so your data will be 16 channel data. So you will get 16 channel EEG data from your brain. So why we capture EEG? Because I already told you we want to identify, we want to detect some brain disorders or neurological disorders. So like epilepsy, seizures, or schizophrenia, or Alzheimer, Parkinson's. So a lot of diseases are there, and people are working on these diseases. And I told you that MEG and fMRI data is also there, but you will see a lot of work is on EEG data. So there are other diseases also for which you can use it. So first of all, when we collect this data, so this data is in signal form. So this is the signal data. So signal data means there are different type of format you can get it depending on the device. And nowadays we are having very good devices so that we can get data in CSV format. So in CSV, if it is a 16 channel data, so you will see when you will open the CSV file, each channel. So of course there is some sampling frequency. So it means in 1 second how many numbers you are getting, how many data you are getting. So if it is suppose 365 sampling frequency, so per second each electrode is recording whatever sampling frequency is there, that many data is recorded by that particular electrode. So if there are 16 electrodes, so 16 into that number of data you will get in 1 second. So in this way that data will be recorded. So of course after getting your data, so I am explaining only CSV data because it is very easy. Otherwise you will have data in different formats, and in that case you will need to convert. For example, as I told you, I had conversation with one of the neurologists in our IMS, BHU. So he has not this simple device. He is having a very big device when we don't get data in CSV format. So that data is in some other format, so we need to convert it into CSV, and then the next stage comes, that is the next stage is feature extraction. So if we want to learn from this data, so definitely we must have some features. So as you know, if our data is image data, in that case we learn some features from that. If we have whatever data we are having, first of all we need to learn some features. So in the same way, if here EEG data we are having, so from EEG data there are generally three ways to find out or extract features. One is time domain methods, or time domain features, frequency domain features, and time frequency domain features. So of course time frequency domain features will give you lot of information. Time domain features will give you only information regarding the time, depending on the time how the channel data is changing. This will be given by the time domain. In frequency domain, it will give you in the frequency wise which frequency is present in your data, not depending on the time. When this frequency is present, when it is not present, it is not there. But in time frequency domain, both of these two informations are there, and that's why generally we use time frequency domain. So these are different ways of doing time domain and frequency domain and time frequency domain. So then there are wavelet transformation methods also. All these methods are basically for feature extraction. So this we have done. We are trying to find out best method so that from EEG if we get some good features, and then we train our model and our accuracy is good. So we have seen lots of feature extraction methods, and we have seen in this case, in this particular in one of my work, we have seen this. I'm just telling you this wavelet scattering transform method, that is time frequency domain method. It works very well. So we have applied three feature extraction methods. All of these three feature extraction methods was wavelet transform based methods. One was continuous wavelet transform, another was discrete wavelet transform, and third was wavelet transform. Wavelet transform method was very well. So on EEG data, nobody else used this wavelet scattering transform method, and we were the first one, and that's why this study was published in a very good journal. So I just wanted to tell you, if any one of you, whoever are working in your, because all of you are teachers, so it is not good for me to give you suggestion. Even then I am giving you suggestion that lots of papers are there, and sometimes it becomes difficult how to find out what should be done in the research. So you see lots of methods are there that are done on different other type of data, similar data, and you check whether that same method is applied there or not. So same we have done in this particular case, and we got a very good results, and that's why this study became very popular. So I have not gone in the detail of this, I am just telling you this. So this was basically open source data, open source EEG data. Total 28 subjects were there. 14 subjects were patients, this is schizophrenic patients, and the remaining 14 were healthy control. So out of these 14 So,
open source means from Gaggle, like Gaggle or similar.
yeah, it was open source. It was, means, we got it in GitHub.
GitHub.
Yeah.
Oh, thank you.
And it was 19 channel data, so it was already given there, and it was in CSV format itself. So for this particular work, we don't need to convert it into any form. So these were the 19 channel data, and then you see we applied some pre-processing techniques. So this was the EEG data. So artifacts removal, some other frequencies that were not matching with the brain frequencies. So when we collect EEG data, so sometimes because of muscles movement or because of electrodes displacement or something, there may be many reasons. Because of that, there may be other frequencies interferences. So we remove those, and then we applied filter. So after this, all these pre-processing, all these noise removal, we have done the epoching. So epoching basically, suppose we have the 5 seconds data we get, and then on those 5-second data we applied, we get the features, we extracted the features. So for features, I already told you that we applied wavelet scattering transform, which was the our method, and these were other methods that already some researchers have applied. So apart from wavelet scattering transform, we have identified some statistical features also, and then 10 cross validation, 10 cross validation we applied because our data set was less, and that's why it was necessary to improve the accuracy or to get the full advantage of this. And in this particular study, we applied 3 types of machine learning techniques. One is core machine learning techniques, that are traditional machine learning techniques, then bagging and boosting. So these are 2 different ensemble learning techniques, and we tried to find out which combination is the best. So this was the one study, and these were the conclusions which are not important. Important was wavelet scattering transform, that was time, frequency, domain features that were extracting, that gave the best results. Then this is another study that we have done. So here we applied machine learning and deep learning techniques to classify depressed patients. So here earlier we were having schizophrenic patient data. Here we were having depressed patients data, and we classify depressed patients with healthy control using same EEG signals. So in this case we applied these linear regression, SVM, and here we applied one deep learning technique also. Since this is the signal data, that's why we applied 1D CNN. We have not applied 2D or 3D CNN. 1D CNN, that's why it's applied here, because the model was signal data. And here statistical field, same after pre-processing, after identifying, after removing the noises, we extracted statistical features, and then in this data set there was also 3 type of activities. Means when this data set was collected, patient was in 3 stages. One in eye closed, another was in eye open, and another was when he was doing some task. He was involved in some task. So for each patient as well as healthy control, they collected data when the person was either closing the eye or opening the eye, as well as doing some work. So we wanted to check which type of data will be more useful if we want to classify, we want to detect whether the person is depressed or not. So in this case, you see, I am not let us see 34 patients data was there. Age range is also given, and this is the again open source data, so you can get this link is also given there. So collected, these signals are collected for each person 3 times, when eye is closed, eye is open, and while doing some task. And sampling frequency that I already talked about. The sampling frequency was 256 Hz. It means for 1 second 256 data for per channel per electrode it was recorded. And so here not filter we have applied, and then Day4 filter we have applied. So these, after this, you see for all three different type of data that is collected for the same person, we train different machine learning models, and it was seen that this is the results of high closed, this is for high open data, and this is the task when the person was doing task. This is the result. So our results are compared with other researchers' results on the same data set. And the main thing is we found that signals which are collected when the subject was doing any task was giving better results for the depressed person's identity. So if they are in a resting state or they are not doing any work, that time EEG data may be similar for the patient as well as healthy control. But if they are involved in some work, that time if they are recording EEG, it would be better to distinguish or classify between these two. Another study that we have done is to find out which frequency, because I already told you there are 5 types of frequencies that are generated in the mind. So alpha wave, delta, alpha, gamma, beta. So it is running this model to study influence of different wave frequencies on variation. Which wave frequency is giving you better? If suppose in our earlier studies we were considering all wave frequencies, but then we have seen in the literature that one frequency is more concerned or your depression patients, one frequency may give you better results. So we have done the same thing here, and we found actually the claim that was done was actually correct. So the motivation I already told you, the objective was to see which brain frequency is more helpful in finding depressive of the data set. So data set is same in this case. Now you see for data wave, so we applied different filters to find only because in your data for all the channels, all wave data is present in the same data set. So we extracted delta wave data, we extracted theta wave data. So in this way, for all 5 waves, we extracted data, and then we trained our model for all different brain wave data. And then we have seen in this particular case, gamma wave, as in the previous study we have seen when person was involved in some work, then that EEG was helpful in distinguishing depressed versus patient healthy control. So you see here also it is giving the same thing, because gamma wave frequency is generated when we are involved in cognitive activities or problem solving activities or doing some activities. Delta wave these earlier waves are when we are in the resting state. So these two studies are giving you similar type of results. When the person's depression, if we want to get the data or for training AI models for their automatically identifying depression for patients, in that case it would be good if we are collecting data when persons when healthy control as well as patients are involved in something, so that gamma wave should be generated there, so that frequency you may get there when we are recording the data. So these are results of with the state of the method. So this is our results and these are other results. So our conclusion was from this study we found that lower range frequencies play an important role while this applying deep learning techniques. Here we have applied deep learning techniques, so that also. And this is also very popular. This is another data set, Day4 data set, and that is also used when researchers want to work on EEG data. So what is this? This is emotion recognition data. So what happens? How this data is collected? There are 4 games. So each and every person was
in those four, they played those four games. So these games were of different nature. Means when one suppose one person is playing first game. So this is monotonous type of game, and that's why you will not generate much emotion that time. There is funny. The second game was the funny game. So another was some where the person will be happy. So this type of different, you can say, games were there that generate different type of emotions. So in that data set, you see 28 subjects were there, 9 female, 19 male, and they were playing 4 games. One first game they labeled it as boring, another is calm, then horror and funny. So that time this data is generated when they were playing these games, and then they wanted to classify from this EEG data whether the actual same emotion your deep learning model is able to detect or not. So in this particular case, this was 5 minutes for each game. So for one person it was 20 minutes whole data. So 5 minutes for each game. 4 games were there. So 20 minutes per patient, per subject was there. And it was 14 channels data. So in your CSV you will get 14, you can say 14 columns. And then you will apply, of course, some feature extraction methods. So lots of, we have already seen there are time domain, frequency domain, time frequency domain, wavelet transforms, a lot of frequency feature extraction methods you can apply. And then these are the models that we have supervised, deep learning models we have applied. So 95% accuracy was there. So you can say that there is a relation because emotions by playing the game we actually generated those emotions and then collected that EEG signals, and then we weighed it for the same level that this EEG is corresponding to calm, this EEG is corresponding to this horror emotion, this is corresponding to, so it is giving me 95% of it. So these are actually we are doing, these are very simple studies where we are trying to check whether machine learning or deep learning techniques can be used for detecting diseases, for diagnosing diseases, for identifying emotions, and there are lots of applications here. It is not necessary always to collaborate with doctors. Of course, we need to collaborate with doctors, but not for whatever we are doing. It will be used for disease prediction in future by the doctor itself. It can be their field of robotics. You can use it in robotics. Simple. You take one. Nowadays, what happening in many labs, robotics labs, they are taking humanoid robots, and then we are training these. We are training robots so that they can help elderly people, they can help autistic children, they can help many things. So how the robot will know what is the feeling, what the person to whom he is interacting, what he is feeling, and so that he can interact in the same way. So this in all these type of simple work we can these things can be done, and a lot of work is going on there. So this was these simple things we are doing here, and these are the regular models. So many what we are already doing, what of us is doing. The second type of work that we are doing in our lab is cardiovascular. So we are also working on ECG data, and I told you the one type of work that we have done, that was we are working on directly on signal data, but since now we are having computer vision field, that is a lot of techniques are there. So many researchers, what they are doing, they are converting the signal data into image data so that those computer vision on this image data and it is giving better results than the single data. So because techniques are very good in computer vision, lots of techniques are there.
I have one more. Sorry. Ma'am, in last PPT you shown that we have taken some sample for the EEG signal.
Yeah.
So the different type of people are having a different type of emotional signal. So if you are taking the different sample size and you are taking the records. So how as a clinical you will justify this record is very much accurate data? Means accurate result in give.
Of course, this was very simple. For emotion, it was not that it will be used in some hospital or something. So here it is not necessary to say whether it is correct emotion is annotated or not. But of course, whatever you are saying, it is correct. That annotation should be correct if we are recording some data. And I was saying whatever data sets I have understood. You see what happens when they collect the data. So they give this data not only to single doctor for annotating, they give it to at least 3 doctors. And if for some reports, suppose annotations are different for different doctors, then they do meeting, they discuss it, and then depending on that they annotate it. So in this way they are doing it.
Actually, ma'am, I work a long time back. I was in Neuro Hospital, Institute of Neuroscience, Kolkata. So I saw that there is a multiple patient having a different type of emotion. So their patient is coming from the different type of situations. Some people have the mentally sick, some are psychologically challenged. So in that time, their people are data will be some changing.
As in BHU, we have different neurological department is there, cardiology department is there. So generally persons having that particular disease, similar type of disease, they are going to that type.
This categorized people are you are collecting from the data.
Yeah, and this is fact that we don't have correct data, and whatever data that are generated in foreign hospitals, and they are not disclosing it because it is
privacy.
Privacy, and in European they generally don't. Even when we go there, we want to take photo, we need to take permission also. So this patient data is very correct, and here also we get because we have some colleagues and personal relations, and so generally it is very difficult to get data. But if they are making it for AI, they are recording it for AI, they do like this. They don't annotate.
Is this called a PRDU of the data?
Of course. At least 3 doctors. Wherever I have seen the review of that data, they have clearly mentioned that at least 3 doctors were, they independently they have annotated, and then if in any instance that annotation was different, then they have done the meeting and then so this was on EEG data, and cardiovascular data. So cardiovascular data, again we are having some image data also, but we are in the starting we are working on ECG data. So again in ECG data we place electrodes in different parts. So one is knee, one right knee, okay. So your data is similar to EEG data. So if it is multi-channel data, so generally 2 lead data when persons start working on, they work on the 2 lead data. It means there are 2 electrodes from there. This ECG data is generated. So again for the sake of completeness, I have this heart and so if you want to work on cardiovascular disease, so definitely ECG is not the only one type of data. There is PPG, echo, ECG, MRI, CT. So there are lots of type of different types of data where you can work on. If you are having expertise in computer vision, you can always work on image data or video data. If you are having expertise in signal processing, you can work on ECG data or EEG data. So it will depend on your expertise on, and it is always better to work on your expertise. because in that case you will be able to give more good points. So in ECG data, I just because we work on this, so I just want to explain which type of data you will get it. Because if you want to work on this ECG data, then from each and every data we need to, when we are applying machine learning models, we need to get some features. So without knowing this data, how do you extract features and then train the model? So your ECG data can be 1 week data, 3, 5, 12 week data. So of course these are how many electrodes are there to collect this ECG data. And then in ECG data you will have P, Q, RS, T. This type of this wave you get. So what happens? This is small P that is called as P wave, and after that there is a sharp peak that is called as QRS. So this is Q, this is R, RP, and this is S, and after that again there is a small peak that is called as T. So this is called as one cycle. So in ECG data you will have these cycles of PQRST. PQRST. So this type of peaks or this type of cycles you will get in your ECG data. So what happens? Of course, if there will be some problem in heart or there will be some cardiovascular disease, so this signal will be different from the normal person's signal. So what happens in that case? There may be some difference in P wave or generally in the width of this QRS wave or this P, peak of this P. So what we are doing, what generally people do, they calculate features like this. Just giving devices I'm giving, I'm giving other type of data and just showing you. These are different other open source cardiovascular data sets. If you want to work on, you can see a lot of MIT BIH is very popular ECG data set, ECG and heart disease data set. So lots of data sets you will get here, but there are lots of other data sets also. Now you see how we do the pre-processing and features we expect from the ECG data. So band fast filtering, wave rate transform, because this is the signal data, so same your pre-processing techniques will be same. But you see here feature extraction we can do like this, RP detection. So one of the feature can be what is the RP? What is the duration between one RP to another RP? What is the you can pick some window segmentation and then from that you can find one cycle. So these are different features. So from this ECG data we find, so first of all we will do the epoching. So suppose we are taking 5 minute data, 5 seconds data, again 5 seconds data. Then from these 5 seconds data we can find out all the R peaks. So all the R peaks can become one feature. Then the 2 R peaks, the differences between difference between 2 R peaks can be another feature. So these are basically your time domain features. How this is changing as this. Read by segmentation, you can segment it so it can become another feature. So this is the simple, very small understanding I am giving for ECG. Although there are lots of other things that can be done here, but this is very simple thing that anyone in the beginning can understand that if we are having ECG data. So in ECG data there will be one P, then QRS, then P, and we can extract features from this and then we can apply machine learning. So of course normalization we need to apply. This we generally do before any machine learning technique or deep learning technique. So we have done it, so that's why it is written. So there is many normalization techniques is being used. And then labeling, so labeling as you told, so in case of cardiovascular disease, generally arrhythmia, there are different types of arrhythmia that are labeled, so PVC, LVVC. So generally we don't get the data for this, but when we see the data set, so you will see for the different duration, one peak, they label it, whether it is the normal After labeling, we will extend the features. So as I told you, RR interval, QRS duration, PR interval. So these are very simple features that you can directly get from the ECG. Otherwise, you can apply time domain techniques, frequency domain techniques, statistical techniques, time frequency domain techniques. So all these things because this is then these morphological features. So after that, after getting these features, you will apply your machine learning or deep learning techniques and then. So when you will, if you will see some cardiovascular data, so disease data, so there will be binary as well as multi-class classification data. So for example, in some data set you will get this is the arrhythmia disease data and this is normal person data. Otherwise, there are data sets where different types of arrhythmia as well as normal person data. So lots of different types of data are there. I think it would be better if I show this because for the starting point where I have shown, I saw no. These are the options. So MIT BIH data set is most famous data set, cardiovascular data set, but you can see other ones. So I am stopping here. If you are having any question, you can ask. Otherwise, I work on many other things. I can tell about them also. But I think there is 5 minutes left, so it is better if you can have some questions.
I have a question that when we place the electrode, so for that there is some noise, maybe for they are not fixing or if the body is moving. So for that case, how we manage all these things?
During pre-processing, we use device it is necessary we should have we used MNE pattern library for that. So in MNE pattern library, you can or you can remove all the artifacts. These noises are called as artifacts in EEG data pre-processing. So we say that all the artifacts are removed during pre-processing. So you have when you start working on EEG data, so you see MNE pattern library is very good library for pre-processing. And apart from that, you can remove, you can use different filters also. So you know what is the frequencies. So you can use low frequency and high frequency. You can remove. So in this way, you remove all the noises.
So as there is a frequency, the domain or the microvolt, the range of this voltage is very low. So is there any external like mobile phone signal and other like any electronic device?
Yeah, it's there. Not mobile. Generally, they take care of that. But because of their instrument itself, there are sometimes these interference of these frequencies also. So, but it is means using you need to apply some pre-processing technique to remove all these noises.
So is it like identified?
Sometimes it happens that you don't know exactly what is the noise. So sometimes there are chances that you may remove your data also. Your noise that is actual signal, but you are removing that also. So you need to take care of that. Generally,
is there any way to put all this electrode inside this brain?
I have shown you there are some invasive techniques also, but generally for research purpose we don't do this. We want to, because nobody would agree to give you data like this.
No, like there is some neurolink or which are developing research is going on through some white rat.
Of course, there are chips are also being developed that will be placed inside our this. Suppose I have heard that it is kept there, so it will be implanted here and then it will record the data. That is done, but generally means For EEG and ECG we are doing like this, and even hospitals are doing like this. Because it will be very difficult if we will use invasive techniques for patients. Means nobody will be agreed to give you research.
And one another thing I have, we have shown the image of the electrode.
Yeah.
So these are very much costly. One is I don't remember the brand name.
Yeah.
Uh,
Brand name?
yeah, like this.
Yeah. How much cost do you think of this?
Yeah, like near 65,000 to like 2 lakhs.
Yeah.
So, is there any way to develop this electrode or combine this electrode in a 3D printed model so why anyone can use this for testing purpose?
I'm not able to understand your question. You are saying that these electrodes can be modeled with your deep learning model or AI?
No. This electrode, if we want to purchase, then this already like there is one image you have shown. That is very costly. I am saying that is very costly.
Yeah.
So this.
It is
So
very costly.
yeah. So can we make this electrode in lab?
Yeah,
In 3D
of
printed
course,
model
when seeded Delhi, I worked with them only on one problem. So I went there and they were developing, they have developed this only 8 channel device they have developed in their lab itself. But they have fund for that also, and they have different, because we are teachers, so we need to do research as well as teaching, but they are full scientists, so they are for that only. They are full day, they are doing the same thing. So they have linked with different industries also, they can order them, and they have done like this. But that was also costly. When I called her, so she told that it is half of the cost, so if it is 2 lakh, that is 1 lakh. Not so much cost effective, but of course it was. And we should, means in any university or institute, we should have these type of labs where students should develop at least not 16 channel EEG, at least 2 channel EEG they can develop. We should have this type of labs. But not only EEG, we can do a lot of things. As I told you in NTNU, that is QS ranking is 52, and there they are having robotics labs, so a lot of humanoids are there, then different types of robots are there, and their students are doing a lot of experiments. They before examination they come and they collect their data, and then they are training robots so that they can interact with the student and they can relax them before examination. They get lots of in their labs they are having lots of these type of tools, and they are doing a lot of experiments. In our labs generally we have computers, so while we should have this type of labs where the students should develop their skills. Recently I went to University of Toulouse, so there also there was one workshop, a fabric lab, that was the name I am just forgetting. There they had a lot of 3D printers, lot of wood cutter machines were there. Yeah, and students were doing all these things. They were creating mementos for many things. There were glasses they are putting there, and some designs will be it will be done on that. So a lot of things. One fabric sewing machine was there. So different reels were there, color thread reels were there, and it was connected with the computer. So design is given here, and T-shirt is kept on the machine, and fabric it will print on the same design that we have given. So it will take the thread and it will print. But students are they are getting everything from different industries. They are assembling it and they are doing it all the things. I asked them, so there was one machine, they were not able to handle it and they were in the 4th year. So they told them, sometimes it happens we are not able to use, but we get this opportunity. So something we do, something that we are not able to do, our juniors will do. But here what we think, we wasted 2 lakhs, we wasted 10 lakhs, our students are not doing, so in the next year we will not do this. So, young generation, we know they are generally in BHU, if we talk about BSc students are very good, MSc students are also good, but BSc students are very good. So if we give them opportunity, this type of developing labs, they will do it very well. And here also, in every place, our young generation is very good. We must encourage them, we must trust on them. We are not doing that. So sometimes it is very difficult. Sometimes we feel very emotional and we are. I want to say many things because just now I am coming from another country and there what I saw, I was in Toulouse, that is one of the city of France, and that was earlier I was in Norway, so that is very, very cold. Every time weather is very pleasant. But so I was thinking, okay, India is like this and the weather is very good. But in France, Toulouse was very hot. Even then, there was not many ACs in all the buildings. Even in the University of Toulouse, in few buildings ACs were there. In many labs and many faculty chambers, AC was not there. And it was, means we were able to manage it. I was feeling that it is like India, and in this situation, generally we sit in AC, generally in our home we have AC, in our labs we are having AC. They told that no, we are managing. Sometimes it is very hard. Or what they are having means each and every person, whether it is a teaching person or administrative person, they are having one small fan that, so they are having this fan and this way they are managing. And you see in roads, lots of cycles were there. So the professor who hosted me, they are both professors, one in computer science department, one in electrical department. Even then, they both, this Philip, who is the male faculty, so he always go with cycle, and Florence, she was computer science professor, so she used metro. They don't want to use car every time. So whenever we went to a restaurant or somewhere, she would, oh, let's go, let's take the walk. So I told, this is very long, and generally we take car in that case because in the morning you are in the university and now it's 8 o'clock. So she told, no, I like walking. So we generally, now I'm thinking, and I started going my department by walk. So earlier I thought, how it is possible? It is half an hour distance from my home. I am living in BHU itself, staying in BHU itself. Even though I am on one corner, my department is another corner. So it is half an hour walk distance. So earlier it was impossible for me to go by walk or by cycle. But when I came from there, I thought, no, otherwise I will become like this after 5 more years. It is better. So I started going by walking, and when I thought that if sometimes it would be delaying, then in that case I will take my time. So because lot of in many conferences or workshops we talk about data centers are creating lot of hot, lot of heat, and in Norway what happens? In the data center, the heat that is generated, that from that heat is means from the pipe, it is gone to the each and every house. So in house you don't need to, because there is temperature, minus 30, minus 40, 50 degrees centigrade. So, but they don't generate heat or they don't have heaters in or any ACs, hot ACs for that. They have pipes, and it is automatically, so they are using like this. In the University of Toulouse also, he told there is a big computer, and in summers behind those countries, and we should think about it. We should definitely think about it because my sister is in Italy. She is staying there from last 3 years. She was telling, when she was telling all these things to me earlier, I was thinking why she always would say like this. And but it is fact. You talk about IIT people, they go there many times, and they when IIT people say when used to say something to me, I was thinking, okay, he is saying like this. I was not confident that he is correct on it. But now I think India is definitely 100 years back. When I was going on Sardar from in the Delhi airport, he told me why you are staying in India. His whole country moved to UK 30 years back, and he told that I told no, I love India. I will not leave India, and because generally I don't feel very happy when I is in if I am in out of India, it's in Norway. Also, I was feeling I should go to my place. I should go to in France also, in Sweden also, because maybe I am 47 years old. So we used to live in different culture, and there we don't see we are when is what we are used to in the evening when we are going home. We want to go for some marketing, we want to go some walk and see street foods and all these things that we don't see there. So for those things means it is necessary for me to live in India itself, because there I feel always I feel I can't live here. So I was saying all these things to him. He told after 10 or 20 years you will feel that you have done the mistake, because this is the time that you can go there. And they are staying in UK, so they were saying that UK has generated 50 years electricity in advance, and what India is having, I don't know what happens here, but in summers in UP,
India is going in deficit.
deficit, of course, that I am telling that in UP, every day in BHU also now at least 10-15 minutes they are cutting that. They cut their electricity. I don't know why. So of course there may be deficiency, and that's why they are doing it. But UK, they have reserved 50 years electricity in advance. So people say like this, that then I think that we are the educated persons, and we should think in this way. And we don't need to do a lot of innovations, and we can't do. But we should encourage our young generation. We should trust on them. We should provide them all the opportunities. Anyway, I have some quotes to show if hands-on session I did. May not run here because I will run it on Colab, but generally because I already told you that the signal data we converted into image data, and then we applied some models. So for that work is high-end computer systems like orchestrations we use. So in my place we have orchestration. already gone over it, but in my slides I have given the link. So you see, I told you we work on some CSV data sets, but this is not the CSV data set, this is EEA data set. So we can't open this data set, although some patient related details and EEG data is written here. So which channel data is this and which, how much, what is the time recorded, based on that, all data is written there, but we are not able to see this. This is in some another form. So that's why I am not able to show it for you. So you need some Python code to open and understand this. So, but I am just showing you. So in the same way, this is also EEA format data. So it is not necessary that if you are having some EEG device, you will always get data that you are seeing in column or in CSV format. So you need to convert, or you can use Python to see what is written in that, and directly you can work on that. And then this is basically feature extraction method. So what we have done, this was the EEG data, so we have converted it into MTF images. So I think that code is somewhere else, and after from this MTF images, you see we have loaded these MTF images, and we have given the labels. If it is 0, then healthy, 1 for schizophrenic patient, and then this is just loading the data set, and here it is converted into, because first this EEG data is converted into image, then it is converted into colored image, so RGB format image, and we are appending each and every image that is generated into this image array. And here VGG16 is used for feature extraction, and then we use some other models for classification. The last layer of VGG16, that is fully connected layer, that is used for classification. You see we have done it as a false, so that classification is not done for that, only features are extracted. So extract features, and this is VGG model we have used here. The images that all the images we have taken in text_images. So these images are loaded, and it is from these images these features are extracted, and whatever features are extracted in X images, all the features are there. Y images, all the annotations are there. Means whether the patient is schizophrenic or not. So we have already labeled it as 0 and 1. So in Y we are having either 0 or 1. And then the same, all these features are saved in CSV file. So you must have some idea of Python and different libraries. So using these, this is the code only to convert, only to extract features from different images. So images are in this MTF image form. So whatever data is there, that data is converted into MTF image, and then from MTF image we extracted features using VGG16. And for classification, then yeah, I can show you. This is the CSV file that is just I showed you that we saved that CSV file after extracting the features. So you see, this is for first person, for 53 it is written. So suppose 53 patient data, and W1 means channel 1. So it is 16 channel data. So you will, for each patient you will have 16 instances, 16 rows. And so in this way, and this class is showing whether it is a normal one, a normal, or it is taking some time to load. Otherwise, if one is written, this is sorry, schizophrenic is written. So when we applied classification, in that case we removed these two features and we converted this particular into label that is 0 and 1. Because we know our machine learning or deep learning technique can't learn from this actual data, so we need to convert it to either we will apply some one more time coding technique if it is a independent features, if it is a and since this is a dependent feature, response feature, so we will apply their labeling. And these are the features. So you see here we applied DGT16, that is one of the deep learning techniques, and that's why it is very difficult to understand what these features mean, and that's why this is a black box. And in DeepMind's tool, I told you that is more explainable, because in the first part we have done segmentation, and based on the segmentation map that we generated, on that we applied machine learning technique. And that's why it is easy for doctors to understand why if it is suggesting that disease is there, so we can see the segmentation map and find out, okay, whatever is suggested by the deep learning model, it is actually correct. But in this case, doctors will not be able to find out whether the your model is correct or not, or why it is giving this particular data. It is not possible because we are having these type of features that are not understandable by us or even doctors also, because they don't know what is the first feature, what is the another feature. We don't have any labels for that. We run means it will not run here because these are very large MDF images, so it will run only on one station. Otherwise, the Colab crash per hour. This is the classification file. So again, after importing all the libraries, and you will see these are the feature files. So after reading those features file, standard normalization is you normalize all the features, and when the standard scalar is used for that, we have another technique also, but here we have applied it. We use k-fold cross validation because the data set is less, so that's why we use this cross validation. So 5-fold cross validation, and then here we applied SVM as well as, so your kernel will be fine there. And early stocking, we use here early stocking also because there was a problem of overfitting. So that's why we thought if we apply this early stocking, there are chances that, and in that case we get better accuracy on test data also. This early stocking, and you see here training and test, train and test data.
Can it be shared in your review? Can it be shared in your review?
This code, only code I can't share. I can share my slides. Why? Because this is our recent work that is published, but we want to extend it. So my student Alka, she worked on it. I can share it because I told her that there is no problem we can share, but she told ma'am I am going to submit my thesis. I will extend it one more what I study I will do after that you want to. So this is the only problem, but I can share my PPT. In PPT all the details are
Can be shared, but
data set is open source data. Data set is open source data. So only code I can't share.
I think it is taken from the title.
Data, no, code is not taken because
No, I'm not talking about the code.
yeah, data set is Kaggle or somewhere. Because session is useful. I don't know whether, because it is very difficult to explain this theoretical work with in 1 or 2 hours, and for you it is very difficult to understand each and everything. I know it is very difficult, but at least I introduced three different fields where you can, if you want to apply machine learning deep learning in medical domain, then there is one this retina diseases, and then cardiovascular diseases, and then neurological diseases. Neurological diseases and this cardiovascular diseases, you have both type of data, signal data as well as image data, and even video data, that echo is also there. And in eye case, you have 2D as well as 3D data. So if you want to work on medical data, you need to have expertise on computer vision, you need to expertise on signal processing, AI, machine learning, and all.
So participants, if you have any more question, you may ask. Okay, so thank you ma'am for such a wonderful presentation. A big round of applause from the audience. So we can see in the presentation, ma'am has very clearly classified her presentation into 3 main parts. In the first part, she spoke about the retina and bio-retinal systems, then AI for bio-retinal signal optimization, where she spoke about DeepMind's AI system and about the gradient boosting algorithm, about the retina, bio-retina. Then in the second part, she spoke about the neurological disorders, how it can be collected using EEG signals. Then she spoke about the non-invasive techniques, in which she briefed about different studies that she has done. Like first one is the wavelength transformation, second study ML and DL techniques to classify depressed patients from EEG signals. Then third study, a deep learning based model to study influence of different brain waves frequencies on depression, and fourth study on hybrid convolutional neural network. Then in the third part, she spoke about the cardiovascular data types, sources, pre-processing and applications in AI research. So thank you ma'am for such a wonderful presentation. Now as a token of appreciation, we would like to felicitate ma'am with a presentation certificate. So I call our principal sir, Dr. Subhashri Sarkar sir, along with the coordinators and the co-coordinators, Mosmi Atta madam and the co-coordinator to kindly come up and present a presentation certificate to the young person.
May I request our Vice Principal Madam, Shobana Madam, to join us?
Yes. So I request Vice Principal ma'am to kindly join in the felicitation. Thank you, sir and ma'am.
I'm very sorry. The first part of my talk I was not confident, because that I am not working on that. I just prepared because it was given, the topic was going to be, but then I thought it is similar to the thing that I am doing. I am working on image or signal. It is retina. If we want to use for disease prediction, definitely we will use some scans that are images, and so I thought I can tell at least something. So I shared it. I don't know how much useful it was.
And then on behalf of all the attendees, all the esteemed faculty members, on behalf of this foundation, again we extend our sincere thanks and gratitude. The session was very rich. During the session also I have received queries from some of my colleagues who would like to be in touch with you, they would like to extend your research. So thank you very much, madam, for your time and the experience.